This is the screencast for section 6.1, example 1, solving differential equations, and we're going to use those to create slope fields and use Euler's method. In this chapter, you're also going to learn how to take integrals by hand, antiderivatives by hand, in a more detailed fashion to get an exact answer, an exact area under the curve. So example 1, we're going to solve this differential equation. This is actually nothing new so far. We have dy dx that is given to us, and that is secant squared x plus 2x plus 5. So if I multiply both sides by the dx and get the differential dy, I can take the antiderivative of both sides. The antiderivative of dy is y, and then the antiderivative of, I can kind of distribute the antiderivative across a plus sign, because remember the integral sign stands for a sum, so I can do that independently throughout this sum. The antiderivative of secant squared is tangent of x. The antiderivative of 2x would be x to the second power divided by 2, and then so that'd be 1x squared, and then plus 5, now x to the first. And then don't forget your plus c. This is not a closed interval, and in a closed interval, you would use the fundamental theorem of calculus part 2, where your c's would cancel out. Here, we don't have any c's that would cancel out because we're not evaluating from a lower limit to an upper limit. The now try problem number 1 says find the general solution to the exact differential equation. So same concept. We're going to multiply both sides by dx to get the differential dy, which is 5x to the fourth minus secant squared x dx in parentheses, so that dx applies to both pieces. Take the antiderivative of both sides, and again I can take the antiderivative across this sum, which is really subtraction but the same thing. So now 5x to the fourth becomes x to the fifth minus secant squared, antiderivative of secant squared is tangent x, and then don't forget your plus c.